Hello everyone, I welcome you all to my YouTube channel. In this lecture we will be discussing about earth resistance test. This test has been divided into two parts, part 1 and part 2. In part 1 we will be covering up the theory behind the fall of potential method. Along with that we will be discussing about some of the connection diagrams for the kit that we use for the site testing. In the second part we will be looking further into a kit 1625-2 by Fluke and try to prepare some connection diagrams, and at the end we will be discussing about the derivations that are necessary to understand the earth resistance test. So let's go ahead and start. In this lecture we will be mainly focusing on one standard, that is IEEE 81, and the version which I will be referring to is 2012. So as per section 8.2 of this standard, there are multiple methods for measuring the earth resistance test. So first one being 2-point method, 3-point method, stage fault method, then clamp on stakeless method, or fall of potential method. Now this method is the most commonly used method throughout the industries and especially in the railway industry. This method is mainly prevalent in small or medium sized grids, and it is required or it shall be done only where the soil resistivity you feel is uniform. So the section where you are testing, the plot area where you are testing, the soil resistivity shall be uniform throughout. Now this method is also called FOP in short form, and further this method is divided into two parts. One is by calculating the average value, that is by the average method, in which we plot the graph, and the second one is the 62% method. Now this 62% is basically 61.8%, but we generally call 62, and this is a mysterious number that many people have asked me how this number has arrived. Why 62? Why not 52? Why not 78? Why not any random number? Why only this? So for this I have done the derivation in part 2. So once I upload the part 2, if those who are interested can look into the derivation at the end. Now before entering into the connection diagram, I would like to explain you the theory and to have the feel of how earth resistance and what earth resistance is, and then by knowing this we can calculate the earth resistance and do the test and all. So I am taking a basic example of a hemispherical electrode. So this is a hemispherical electrode, and this is your ground. About hemispherical electrode, I have done some derivations in earthing bonding lecture 2, which is very interesting. For those who want to go deep into it can refer to this lecture. In this I will be just doing the basic derivation and explaining why this method is called fall of potential. So this is your ground, this is your rod. In case of fault, the current will enter into the rod and try to split and flow in all the directions. So whenever the current flows, it flows and goes ahead forming equipotential surfaces. So this current will go ahead and form equipotential surfaces till it reaches some point which is the infinity. After that it is same. So here if you see, there will be some, this surface will be basically, I'll draw like this. This surface will have some equipotential, this will have some potential which will be equal throughout. Then this surface will have a different potential and it will be equal throughout, and then this surface will have an equal potential. So all the potential in these points will be V1, V2, V3, which will be same throughout. V1, V1, V1 here, V2, 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 V3, 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 and this will be in a hemisphere. So don't assume this as a semicircle, but it will be hemispherical in 3D shape. Now, why once it goes, and the current will always flow from higher to lower. So V1 will be greater than V2, will be greater than V3, and at the end there will be a point coming like V4, V5 and V6, and you reach the source. So maybe there will be a point after some distance which is termed as infinity. This point V4 will be nearly equal to V5, will be nearly equal to V6 because the distance has increased so much. Now if we see what is the effect of this distance on this resistance, we will check. This resistance formula which we know is only one, that is rho L by A. And why we are trying to understand resistance? Because this is the only quantity which we are going to measure in the test. So first let us derive what is the resistance of this electrode. Now resistance is rho L by A, this everybody might be knowing. Resistivity of the material, length of the wire, and A is the area of cross section through which the current is flowing. If we apply this formula here on the electrode, we fail because at 1 the area is different, because here the area will be A1 for this curve because current is going through it. So this is your cross section area. Similarly for this yellow orange curve it will be area 2, and for this it will be area 3. Each time the area is changing. Here the area of hemisphere will be 2 pi, suppose this distance is x1, so it will be 2 pi x1 square. For area 2 it will be 2 pi x2 square, then it will be 2 pi x3 square, and so on. So it keeps on changing. I cannot write this formula. Then what to do? Then what we will do, we will take a small element. In this case we will assume that this is your hemispherical electrode of radius r. We will assume that at distance x there is an equipotential surface, and then at x plus dx again there is another equipotential surface. But what we assume here is that the area for this, let us be A1 and this be A2, is nearly same. That means A1 will be having an area 2 pi x square, A2 is having an area 2 pi x plus dx square, but this dx is so small, that is it is tending to 0, that area of 1 nearly is equal to area of 2. By doing this what we achieve? We achieve that we are able to write a formula for resistance. Now we can write a formula for this small part. dr will be equal to rho. Rho here will be the resistivity of soil because current is moving through soil. Then length which the current is traveling is this dx thickness, so length will be dx, and area of cross section through which it is flowing, A1 or A2, it's same, so we can write 2 pi x square. Now if you want to calculate the true resistance, it will be from the outer surface from where the current started leaking with respect to earth. So outer surface is at r from the center and it goes up to infinity. So if you integrate this formula will come out to be rho upon 2 pi r. However, if you want to know for x what will be at x distance, so you can do it from integration from x to infinity, that is from this point to infinity. So resistance at x for this curve, it will be rho upon 2 pi x. So if you want to know what is the potential at this point Vx, it will be nothing but current, which is the fault current here, times the resistance, that is rho upon 2 pi x. And this x, if you see here, is inversely related to the voltage. That means as x increases, V decreases. That means x increases, the distance increases, potential falls. So that is why we term this method as fall of potential. So if you see the curve, it will be like this, potential versus distance. As the distance is increasing, the potential keeps on falling. Now, this is mathematically we have understood this now. Now if this x is at infinity, it becomes, the potential will become 0. Infinity can be any distance very far. So if rho upon 2 pi, let us suppose distance is 10 meter, there will be some value, 20 there will be some value, but if you take very high, 100 and 110 or 200, then this value will be not enough and it will be nearly the same. So at infinity we will reach and we will get the true resistance value. Now to calculate, we have done the calculation, we know the resistance formula, we know everything now, but how to measure it? What we have calculated, is it correct or not? How to measure it? So for this we use Ohm's law. Ohm's law is V by I here, we will get R. So we need to inject some current and then measure the voltage. By doing this, we will have something with us and that will be the resistance here. So let us suppose this is your ground and this is your earth electrode, which is buried in the soil at suppose depth L. Now we have to inject a current, so we must have a current source, and we will connect this current source to this rod. So the current will flow into the rod, leave the rod, and try to go back to source, but it will see, oh, there is no connection here. How to go back? So for that, what we need to do, we need to install one more rod, that is called the current probe, that will be responsible to collect the current. So this current probe we have installed. Now this will see, oh, there is a metal here, I will try to go near this, but it has to go back to its source. There shall be one more connection, so we will connect this to the current injector. With this current which was flowing will go back to its source. So it will travel through the earth and go back to its source. Now to measure the potential, because once the current is entering here, it will form some equipotential surfaces near this point. It will form some equipotential surfaces near this point. Till infinity it will form. Let us suppose infinity for this rod is till this point only, and then it will form some equipotential surfaces for the other brown rod which we have installed, which is the spike or the current probe. It will have some equipotential surfaces here. This is your current probe, we term it as CP. So for potential we will install one more rod in between. Let this be of purple color, which will be here away from both the equipotential zones. So they have some potential zones inside. If I put here, then there will be a problem, because this rod will have some potential, it will not be infinity, it will not be zero, that is at infinity. Here if I put, again some problem. So in between I am putting somewhere. I will tell you where we have to put, I am just explaining here. So we will put somewhere here, and then we will complete the circuit. We will connect one wire from here. I am sorry for the thick wire. So we will connect the wire from here, use our potential or voltmeter, and measure the potential between earth rod and the potential probe. So this is called PP, it is known as potential probe. Now we have I, we know the current is fixed. We have V, we will take some measurements at different locations of this potential probe. We can install here at random locations. I will tell what are the locations, and then we will plot a graph and we will get the value. So this is basically a connection diagram to understand. Now what happens with the kit? So normally we have a kit. First we will understand the average method. As we saw earlier, there are two types of method, average method and 62% method. So now I will explain through average. Let us suppose there is a kit here which is having 4 points, 4 selections which we can make, that is C1, P1, P2, C2. C1, C2 is current, as you can easily read. In Fluke and in some devices, this C1 is also termed as E, and C2 is also written as H. So C1 can also be written as E or C1, P1 is written as ES, and P2 is written as S, and C2 is written as H. And then there is a selector switch, that is a start button. This is your start button to start the test. This is a typical kit. Now again we will make a ground rod here. So we have our ground rod here. Then this ground rod is of suppose certain depth, that is L. Then we have to install our current probe. So this current probe, again I will take brown color, and we have to install at certain distance. Now this certain distance is what? This certain distance is sometimes mentioned as 100 meter or 50 meter or 40 meter in different manuals. Don't go by that. Just follow the simple rule which is given by IEEE 80 section 8.2.2.4, that typically for a rod, this distance shall be the largest dimension of the rod. So if suppose there are 2-3 rods, L1, L2, L3, we will choose L3, which is the longest one. And the rule says the distance shall be greater than or equal to 5 times the length of the largest rod. So largest rod here will be L3, here it is only one rod L, so this shall be greater than or equal to 5L. So if my length of rod is 10 meter, this shall be greater than or equal to 50 meter. If you choose 100, it is not a problem. If you choose 20 or 10 meter, it is a problem. The results will not be same because these equipotential surfaces will combine. This purple and this orange one will combine. I will show you later on what happens with probe spacing. But just remember, the rule is given by IEEE 81 and in clause this, which states that D shall be greater than or equal to 5 times the L. Now this is your current probe. Typically the depth of this current probe is 6 to 12 inches. You can go deeper in case your resistivity of the soil was higher, but this much is enough to get the values. Now we will do the connections. One thing we forgot to install is our potential probe, but I will tell you where to install. So potential probe, normally in average method we install at 40%, 50% and 60%. Typically at 3 locations, but you can do at 5 to be on safer side, that is 40, 45, that is 40, 45, 50, 55% and 60% of D. So this is your D. If D is basically 50 meters, then you have to choose a length 40 meters for the first rod, 45, 50, 55, 60. So these will be your basically 5 points which you have to choose. And this can be one rod only. You can just do one reading here, then remove the rod, do one reading, remove the rod, do one reading and remove the rod. Now for average method and the graphical method, there is a difference. So you will take these positions, but for graphical, what we typically do, we install the rod at basically at every 10% of the value. So 10% of D, 20, 30, 40, 50, 60, 70, 80, 90. So we have installed at these locations. Now we do the connection. So connection is like, this is your earth rod, it has to be connected to current source, that is C1 or E. So this is my connection which I was showing here, and C2 will be connected to this point, that is at H or C2, and here it will be at the current probe. Now at the potential probe we will connect this P2, so this will be connected here. What will happen to P1? So now there are two types of method, one is 3-pole method and one is 4-pole method. So in 3-pole method we no need to do anything, P1 is left alone. In 4-pole, which is more accurate and has better resolution, you no need to do any other type of test to get a lower value. So here we install this P1 and connect it same to as C1. So we bring a cable and connect it here. So they are basically shorted. Either you short here, but this is not correct method. So better is to short at the pole or the electrode itself. So C1, P1 are connected, P2 is connected to the potential probe, C1 there, then you press start. There is a selector switch for 3-pole or 4-pole. So now if you are connecting P1, you will do 4-pole. So you will do on 4-pole and you will get some value. So with this you will have some value for this point, that will be R1, R2 for the second point. So in this case what you will do, you will remove this point. You will remove this P2 from here, and what you will do, you will connect it to point number 2. Then again you do the test, remove from here, connect it here at 3, then at 4, then at 5, then at 6 and like so on. R4, R5, R6, R7, R8, R9. So I will have some values. So I will plot a graph with respect to distance. I will get a value like this. So this section, this range which I am talking here, this is the range. Here this will be parallel to x-axis for some portion. Not exactly parallel, but nearly parallel to the x-axis in this portion. So this portion is your true infinity. This portion is your true infinity has been reached. So typically it is out of the influence of this rod. So till this point it was affecting, maybe, let us suppose, and this has also its own curve, so it can affect somewhere till this point with its equipotential zones. So for this, these 4-5 rods which you have are nearly in this region. For remaining, you will have lower values here and higher values here. So as you take near R1, the potential difference is low because you are subtracting this point minus the nearest point. The potential difference will be lower between V minus V1. V minus V2 will be a bit higher. V minus V3 will be a bit more higher. So the value goes on increasing. Then it remains stable for V4, V5, V6. The difference nearly remains the same. As it is out of the equipotential zone, it is typically 0. Then again it enters into V8 and V9. So you measure the voltage difference V minus V8, V minus V9, which will be much lower, which will be much higher because V8 and V9 are much lower. So with this, the resistance will be very high. But we have to focus only in this region. And we typically take the average value of these 4-5 values which you have got. So that is why, let us suppose we have this R4, R5, R6, R7. Let us suppose these are the, typically it is till R3, if you will see, for till R6, and then you divide these values by 3, and this is your true resistance which you want to calculate, or the earth resistance. Else what you can do, you can take directly these points, that is 40, 50, 60, just add 2 more, 45, 55. With this you can take the average of these values. So value at R 0.4 plus R 0.545 plus R at 0.5 and so on, and you take the average of this and get it divided by 5. So from this you will get the value of resistance. Now if you are not able to get this thing, that is the resistance is nearly not the same, that is R4 is not nearly equal to R5 is not nearly equal to R6, then you have selected this D thing incorrect. This D is not following the rule which has been stated by IEEE, and you have to increase the distance, or else there is some interference in between which we will discuss in the next part. So we have to check for that. So R4, R5, R6 shall be nearly equal to same. That means it shall be, if the value is 1 ohm, here it will be 1.1, it will be 1.15, like that, nearly equal. All three are nearly equal, then we can take the average dividing by 3. If R4 is 1 ohm, R5 is 2 ohm, R6 is 3 ohm, then you cannot take this average because this will be a bit incorrect value. This will not be correct. So you have to increase the distance. So check whether the values are nearly same. This will be nearly same for low resistance. This can be okay for high resistance, but just check if the resistance is not varying much, typically it is in this range, then it is fine for you. Now, what does 62% method say? 62% method is a simple method which is following the same rule which is we have followed here. Again we draw our electrode and we draw our current probe, when we draw our potential probe, but this potential probe we have to position at 62% of D. That is what this method means. So if this distance is D, so this shall be 62% of D. And again we can do the similar connections, C1, P1, P2 and C2. We will connect this to this, P1 if you are doing 4-pole, P2 to here and C2 to here. With this we will get some resistance value at 0.62 D. This will be the resistance value, and we can write the value here. Whatever we get, this will be your true earth resistance. Now to verify whether you have taken the D correct or not, you can do at 0.52 D, that is place the potential probe here at 0.52 D. So that time you will remove this connection from here and will make a connection of P2 here. Another value you can take at 0.72 D. So if you check, the value shall be nearly same. So this, let us suppose this is R1, R2 and R3. So R1 will be nearly equal to R2 will be nearly equal to R3. When it is there, then whatever you have selected at 62% is nearly correct. Some people take the average of these three and some go with 62% only. Both are correct, but as per the standard, they define it only at 62%, and that is what you can take. Now with this, we have covered the main topics, how we do. In the next lecture, we will be looking into the derivations and the understanding. Here is the clause which I will explain later, and about probe spacing and what are the different errors which can occur, then interferences, and then this is the kit we will be discussing into more. So here you can see this is your C2 which we have been seeing, C2 or H, P2 or H. This is fluke 1625-2, and then this is P1 or ES, C1 or E, and this is your start button which you have to press, and this is your 3-pole and 4-pole selector switch which you have to check. We will be discussing more about this into the next lecture. Just remember, for that the guidance is 5 times the length, so D must be greater than equal to 5L. In case it is a grid or an earth mat, then you have to take the diagonal distance, and let us suppose this is capital L. So in this case, D must be greater than equal to 3 times capital L, that is the diagonal distance. So this is what we take. This is given in figure 22 of the standard, which we will discuss in the next lecture too. So I hope you enjoyed this lecture, and I ask you all to please subscribe to my channel, and God bless you all.